So while you're doing that, let me try to write down what we did last time. And that's all in your handouts. So first of all, we're looking at root systems. So root system is a collection of vectors such that there's 3 axioms. One is that if you intersect with the span of any root, you get plus or minus that root. And another one is for any root, the reflection along that root preserves the root system. And the third one was that the dot product of any root with any alpha check, where alpha is a root, is an integer. Right? And so that's basically the definition. It defines these collections of vectors, and then I also gave you the classification. Complete list, which I'm gonna write down here. So there is type AN minus 1, which is EI minus EJ, where I is not equal to J. And there's also type BN, CN, DN. So first of all, let me define DN as plus or minus EI, plus or minus EJ. And then Bn is Dn together with plus or minus EI, where I is a basis vector, and Cn is Dn plus or minus twice EI, where I goes from between 1 and n. And there's also the 5 exceptional root systems, E6, E7, and E8, and F4, and G2. All right, and you can see some pictures of type A2, B2, and B3, C3, D3, and A3 in your pictures, and that's on this side of the handout, and on the other side you see this is the E8. So the E8 root system lives inside the 8-dimensional space, but here's an orthogonal projection on a certain special plane, on a 2-dimensional plane inside the 8-dimensional space. And these are all pictures from Wikipedia, by the way. And what are you supposed to see in these pictures is that root systems are incredibly symmetric. All of these vectors in all these pictures look sort of the same. There is a transitive group acting on these vectors. And that's sort of what this definition tries to capture. So if you just look at the classification, well, I don't know what you're thinking, but I'm going to think that this is some ugly mathematics. Right? If you see like 4 infinite families and 5 exceptional things, that means you're not doing something right. But what I actually think is true is that it's kind of the opposite extreme. These are all very, very, very special and very, very symmetric. And these are the only ones now that are so symmetric. So yeah, anyways. Any questions so far? Oh, and by the way, I should mention that, so this is the classification of finite root systems. There is also classification of finite reflection groups. Each of these is going to give you a finite reflection group, but there's going to be a few more. There's a bigger classification, which includes all of these and some other reflection groups. All right, and okay. Now, my goal is to try to discuss permutohedra inside root systems. And before I do that, I need to tell you some facts. First of all, remember we have the while group and, well, objects associated to root systems. The while group is just the group generated by reflections orthogonal to my roots. And let me also define V to be the span of my root system, and R to be the dimension of V. So I take the linear span of all roots, which, let's say in the case of A n minus 1 is going to be n minus 1 dimensional. So it's convenient to define A n minus 1 as living inside R to the n, right? But then the actual span of the roots is going to be of dimension n minus 1. And that's going to be the rank. So that's called the rank of my root system is the dimension of the span of roots. And so all of these are supersymmetric configurations of vectors. And it turns out that it's convenient when you work with root systems, it's convenient to break the symmetry. You choose a way to break the symmetry, and then all such ways are going to be somehow equivalent. So let me make it precise. The claim is that there is a way that exists a basis of V, which consists of simple roots. Simple roots are denoted alpha 1, alpha 2, all the way up to alpha r. These are elements of my root system, roots, such that the main property of these simple roots is that your whole root system becomes a disjoint union of positive roots and negative roots. So every root is either positive or negative. And where a root is positive, if and only if it is a positive integer, well, and a negative integer combination of the simple roots. From 1 to r, each ci is a non-negative integer. And similarly, alpha is a negative root if and only if where each ci is non-positive. And already that is pretty surprising. I don't know about you, but I wouldn't expect this to be true. Because if you have a random collection of vectors and you choose a basis, then each vector is going to have, well, usually it's going to have some positive signs and some negative signs when expanded in that basis. And especially you don't expect them to be integers. But somehow for all root systems, just it comes out of this definition after some work, that the whole root system is going to be subdivided into positive and negative roots like this. So for example, let me try to give you some examples. Maybe take type A2, which, as you see in your pictures, is the vertices of the hexagon. And I'm only going to draw the positive roots. C plus is, and it's always going to be 1/2 of all of the roots. Each root is either positive or negative. And of course, flipping the sign of each root takes it from positive to negative and vice versa. So, and okay, so let's say this is the system of positive roots. Which ones are the simple roots? Oh, okay, nice, all right. Alpha 1 and alpha 2, okay. You can't make this guy a positive root because then this, like one of these is going to be the difference of two simple roots. That's not good. So this is alpha 1 plus alpha 2. Yeah, and somehow this the simple roots are, what you do is you choose some generic hyperplane, and then the simple roots are the ones closest to the hyperplane. All right, I can do type B2 pretty easily as well. Here, the positive roots look like this. And then again, alpha 1, alpha 2. And then what I'm supposed to see that each of the other roots is a positive integer combination of the simple roots. And indeed, this is alpha 1 plus alpha 2. This is 2 alpha 1 plus alpha 2. So it works. And what about type G2? Hmm? Yeah, there's one simple root is going to be short, and another one is going to be long. And, well, I didn't draw it properly. Proper picture should look like alpha 2. And then you can write down all these other roots. So this is alpha 2 plus alpha 1, alpha 2 plus 2 alpha 1, alpha 2 plus 3 alpha 1. And what about this? 2 alpha 2 plus 3 alpha 1. Nice. Yeah, so you see I'm getting all these coefficients are positive integers. Pretty cool. All right. And I'm going to try to not erase this for a while. Okay. And what about in general, for general, let's say type n minus 1? What are the simple roots? Every positive root? No, you have to choose exactly a basis, right? You have to choose n minus 1. Yeah. Adjacent, the ones corresponding to adjacent indices. E1 minus E2, E2 minus E3, etc. En minus 1 minus En. And then you can check that. So these are the simple roots, and the positive roots are Ei minus Ej, where I is less than j, as opposed to I being not equal to j. All right, and you may wonder how much, let's say we choose simple roots and positive roots, how much depends on this choice? And the answer is nothing depends on this choice, because act the while group acts transitively. In fact, not only transitively, but what is called simply transitively. The elements of the while group are in bijection with all systems of simple roots on all choices of simple roots. So in your pictures, you can try to practice using some system of simple roots in each case, and then using some other one, and then finding a sequence of reflections which connects one to the other. No matter how these properties already they give you something that's also completely symmetric, even though you break the symmetry. All right, and that's one piece of notation I have to introduce. And let me also introduce another one, which is also sort of important. fundamental weights, which are denoted omega 1, omega 2, all the way up to omega r. And what these are is just basically they are defined by the condition that they form a dual basis to the simple roots. Although not quite as a dual basis, what they are the unique vectors such that omega I dot product with alpha j check should be equal to either 0 or 1, delta ij. 1 if I is equal to j, and 0 otherwise. So, for example, let's try to look for some fundamental weights in my pictures. So let's say I take this type A2 picture. Where would the fundamental weight be? Or let's say omega 1. Where is omega 1? Somewhere over here. And it has to be orthogonal to alpha 2. That's right. It has to be orthogonal to alpha 2. So it has to be somewhere on this line orthogonal to alpha 2. And where exactly on that line? Has to make a right triangle with alpha 1. Oh, interesting. The right triangle. Is that actually? I wonder if that's true. So you want the picture to look like this. You want it to look like this. Okay. Right. Okay. And actually, let's see. So if you draw alpha I, right? Then I can draw the hyperplane orthogonal to it. That's the dot product with alpha I check. Let's just call it alpha is 0 in this case. And then what if I draw this hyperplane that passes through the endpoint? Then the dot product with alpha check is going to be what? On this hyperplane. Alpha check. Okay. Which is 2. All right, that's 2. Yeah. So if you want the product to be 1, that means you have to project onto the midpoint alpha. So in particular, in this picture here, what's going to happen is, well, let me try to draw the picture. So there is, if I just connect these two endpoints, then the fundamental weights are going to be on this line. This is omega 1, this is omega 2. Okay, and you can do similarly. You can, yeah. Let's practice some more. What about type B2? Where is omega 1? Okay, the same idea. It has to be orthogonal to alpha 2, and then, okay, it has to project in the middle. All right. And where is omega 2? All right. Yeah. So for type B2, these two are orthogonal and these two are orthogonal. Yeah, because these are the diagonals, the vertices of the square, and these are the midpoints. There's a square. So where is omega 2? Midpoint of alpha 1 plus alpha 2. Yeah, actually, it's not quite right. It's going to be, because it has to project onto the middle of alpha 2. So it has to be the whole alpha 1 plus alpha 2. This is omega 2. And this is omega 1. Omega 1 is half of the corresponding root. Yeah, and similarly, okay, so for type G2, I guess I'll just, or maybe somebody can tell me, yeah, what is omega 1 and omega 2 in this picture? Oh, this is just the whole vector? Okay. Yeah, that's right. That's omega 1. And what is omega 2? Hmm? The vertical, the whole root again, right? Okay. Yeah, that's true. Thank you. Okay, so this is omega 2. Okay, so you see, you can actually, based on this definition, you can figure out omega 1 and omega 2, and the shorter alpha 1 is, well, yeah, anyways. The longer the root, the longer the omega is going to be. So finally, what I'd like to introduce is the what is called the while vector, which by definition is denoted rho, and it's just the sum of all fundamental weights. And or in other words, because once you know the expansion in the fundamental weights, you know the dot product with any alpha check automatically. So this vector is characterized by the condition that the dot product of rho with any alpha I check is equal to 1 for all I 1 up to r. So I can draw, if I just sum up the fundamental weights, this thing is going to be rho, and here rho is going to be somewhere here. All right, so this is the nice while vector. And why is it? Let me tell you one cool fact about this while vector. Cool fact about the while vector is that it is equal, rho is equal to 1/2 times the sum of all positive roots. Which to me is a crazy statement, because it holds for all root systems. You know, let me show you an example. Maybe I should, yeah, maybe let's say if I look here, I take the sum of all positive roots, alpha 1 plus alpha 2 plus, well, sorry, alpha 1 plus alpha 2 plus alpha 1 plus alpha 2. So I get here, that's twice rho. And then rho is 1/2 of the sum of positive roots. Okay. And if I look here, then rho is here. Yeah, let me actually try to, I wonder if I can draw. So if I draw a square, I don't know how many I should draw, but let's say This is alpha 1. This is alpha 2. Right, and then I also have these roots here. And then I take alpha 1 plus alpha 2 plus the vertical root plus this diagonal root. So this point here is going to be twice rho. And then rho is going to be the midpoint of that line segment. And that's what you actually see if you sum up these two things, right? And rho is the sum of this is omega 2, this is omega 1. So you sum up and you get rho. So this is a mind-blowing fact. Like it's, yeah, try proving it from the axiom. It's going to take a while. And their chalk. All right, so that's the root system background that I would like to introduce. And now let's go back to permutohedra. Because remember, when you say intuition, you mean what's the proof or proof idea? And yeah, I don't know. I mean, it's an important vector for me, like from the Lie algebra's point of view, it's an important vector. But yeah, I know it's completely unexpected that these two would be, that this vector should have dot product 1 with every alpha check, alpha I check. Yeah, I mean, I understand your question, but yeah, it makes sense that if you sum up all of these, then you get dot product 1. But why on earth would you take the half, the sum of all positive roots? No, but there's many more alphas. It's not just the simple roots. I'm summing all roots. So it's, yeah, it's. I don't have a conceptual explanation without going deep in. Well, I mean, it's not. Yeah, so let's see here. If you take the sum of all positive roots, it means you take alpha 1 with coefficient like 1 plus 3 plus 2 plus 1 plus 3. Well, you don't take the negative ones into account, right? You're only summing the positive one. Yeah, there's I don't think there's a simple proof of this fact. That's why I call it the cool fact. Yeah, and oh, by the way, I should also mention before I finish with this, let me try to find the fundamental roots of type a(n minus 1). So type a(n minus 1). Now let me write down the simple roots. Alpha 1 is, it has coordinates 1, -1, 0, 0, 0. And then alpha 2 is 0, 1, -1, 0. Alpha 3 is 0, 0, 1, -1, etc. 0, 1, -1, 0, 0, 0, 1, -1, 0. Okay. So how do I find, let's say, omega 3? Omega 3 has to be orthogonal to all of these things and to all of these vectors. But it has to have dot product of 1 with alpha 3. Okay. 1, 1, 1, and then you want 2, 2, 2. Wait, actually, okay, well, let's try 2, 2. So it's good. It's orthogonal to all of these. That's right. and then it's also orthogonal to all of these. Instead of 2, put -1 here. Put the 2's first and then the 1's. Okay, let me try that. 2, 2, 2, 1, 1, 1, 1. Yeah, then indeed the dot product is 0 here and 0 here, and it's 2 minus 1, which is 1. Okay, that works. And notice that you can actually start with like 3, 3, 3, 2, 2, 2, 2, 2. Or let me even write 1, 1, 1, 0, 0, 0, 0. But either way, it's not exactly the fundamental root because fundamental weight, because the fundamental weights are supposed to lie in the span of roots. Right? They're supposed to lie inside V, and V is the span of all roots. So I'm always gonna think of omega in type AN as just this vector here, but what you should actually keep in mind is that this is not quite true. And the actual formula for omega k is, 1, 1, 1, 0, 0, 0, 0. There's k ones and n minus k zeros, but then you have to subtract the constant vector. You have to subtract the sum of these coordinates is k. So you have to do k over n times something like that. Or sorry, yeah, I think. Just to make the sum of coordinates equal to 0, you have to subtract a vector which is orthogonal to all roots of my. All right. What is okay or all right? All right, so back to permutohedra. And let me remind you what we had for the usual permutohedra. Basically, in type AN-1 is what I want to say is that the standard permutohedron is, well, first of all, so there is kind of 3 interpretations. It's the convex hull of XW, where W is in the symmetric group, or it is the more or less some constant plus the 1/2 of the sum of the sum over all of these positive roots, right? The sum of line segments. Or it is also a constant plus the sum of the Minkowski sum of all hypersimplices. Okay, so here's a question for you. How do I generalize this to arbitrary root systems? Yeah. Okay, interesting. All right, so here you want to say that I want to, the way I chose notation here is that it directly generalizes to all root systems. So for arbitrary root system P, indeed I have, this thing becomes still 1/2 sum over all positive roots, negative alpha, comma alpha. I can take this as the definition of my root system permutohedra. Okay. What about the other two definitions? Ah, okay, interesting. So you want to say that the first definition becomes that the root system permutohedron should be the convex hull of W of X. So let me actually define it. Let's say you choose, let X be a point in my span of roots in my ambient space. Then the permutohedron of X is the set of all the convex hull of all points obtained from X by acting by elements of the while group. You start with X, and then you reflect X in all possible ways along these hyperplanes. And okay, interesting. But then that depends on the point X. You can, maybe I should try an example. Let's say I take this root system here, and I draw the orthogonal hyperplanes. I'm going to get something that looks like this. Supposed to be 60 degrees everywhere. And then if you choose X to be some point, then let me draw it properly. If you choose some point X, then you reflect in all possible ways. You get a hexagon, but it's not a regular hexagon. It's some weird hexagon. Or maybe it's not even, yeah, you can choose X to be on one or several of these hyperplanes, and then it's going to be a triangle in this case. Yeah. Okay, so you want to match it to this definition here, right? Or what? Oh, okay. Oh, is it different actually? Let's see. So indeed, in type AN-1, I don't know, would you? So let's say I take X to be 1, 2, all the way up to N, right? And then I want to apply, let's say alpha is EI minus EJ. And then I act by S alpha on X. What am I going to get? Right, it's going to be right. So, but it's interesting. Like it's in type AN, in type AN-1, you have these natural coordinates. So you can take X to be 1, 2, all the way up to N. But in other root systems, there is no very natural choice of coordinates. Like, I mean, in type B and C, etc., I gave you some nice coordinates, but yeah, let's actually, I wonder if we can, let's say you take, yeah, I wonder if this actually, yeah, I mean, it's an interesting question. Like, what is 1, 2, all the way up to N in type E6? Is it, and there is no natural choice of coordinates on E6, which would somehow there are several choices you can make, but the E6 is itself unique as a root system, but you can put coordinates on it in different ways. So you can't really directly, the only sort of coordinates you can appeal to are, let's say, coordinates in the simple root basis, fundamental, like some dot products with fundamental ways or something like this. So yeah, and it's a good idea to try to understand what is this vector in an arbitrary root system without using coordinates. Oh, interesting. Is it the sum of all positive roots? Let's see if I take the sum of all positive roots. This is ei minus ej, ei minus ej, where I is less than j. And what am I actually going to get if I just take the sum of all positive roots of type a n minus 1? Oh, actually, no, that's not true. I'm not. If I sum out the simple roots, I'm going to get e1 minus en. But if I sum all positive roots, okay, it's n times e1 n minus 1 n minus. I'm sure it's n. I think it's n minus 3. Or because it has to like, okay, so for e n, the coefficient should be negative, right? And yeah, so okay, so you don't get exactly that vector. Well, sort of after a constant shift, what you get is twice that vector. If you okay, so if you take half of that, then what you get is a shift of this vector by a constant. And that's the wild vector. Okay, yeah, very nice. All right, good job. Yeah, that's the, and you can actually see, if you want the permutohedron at the end to be equal to this Minkowski sum, then one of its vertices has to be the sum of all positive roots. So the actual let me call it fact number 2 prime, because the fact number 2 was that the permutohedron is equal to this sum of line segments. And then fact number 2 prime is that if you take the permutohedron of your root system, where you take your vector rho to be the one you're acting on by the wild group, then this is on the nose equal to the sum 1/2 of the sum over all positive roots of these line segments here. So you can actually check it. So let's say I take type B2. I take type B2, and so I'm going to draw the corresponding hyperplanes. Then well, I have to take rho as my original vertex, and then I have to reflect it in all possible ways. So let's see. Rho is somewhere here. And then it's kind of closer to this vertical line than to the 45-degree angle line. So I get an octagon, which is not regular. Sort of. These sides are longer than these vertical sides. And then this octagon, according to my fact here, is supposed to be the sum of how many line segments? 4, right? Because there's 4 positive roots. And indeed, I take the sum, and I get 2 short line segments plus 2 long line segments. And you can check that if I sum up these 4 line segments, I'm going to get an octagon with exactly the same side lengths as here. Okay, and finally, what about the other definition here? Any ideas how to? Because I have to confess, actually, before I taught this class, I didn't know about this. I was wondering whether this is true, and actually turned out to be true. So I was kind of surprised pleasantly. Anyways, how do generalize hypersimplices to root systems? This question is actually tricky, but let me give you a hint. So let's say I look at the vertices of some hypersimplex. The vertices are, what are the vertices? K1s and n minus K0s permuted in all possible ways. Okay. So what is the meaning of K1s and n minus K0s in type A n minus 1? Fundamental weights. Nice. Okay, it's right here. Each fundamental weight in type A up to some shift is just K1s and n minus K0s. All right. So what should be fact number 3? What should be the generalization of this interpretation of the permutohedron? Or of the hypersimplex, let's say. Oh, okay, nice. Yeah, that's so you can just generalize fact number 3 to all root systems by just saying that the permutohedron of rho is the Minkowski sum of permutohedra for omega 1 plus omega 2 plus all the way up to omega r. And again, all the shifts work out exactly as they should in each of these cases. Because you know rho is the sum of fundamental weights. And you know rho is half the sum of positive roots. So there should be no shifts in either of these pictures. And that's actually, yeah, so maybe I should try the octahedron again. Oh, sorry, octagon. Well, I can try the octahedron too. All right, so for the octagon, I have this. Yeah, if you write, you mean in this type A form, right? Or okay, yeah, it's a lot more. It becomes natural, and that's what happens in general. If you generalize to root systems, you understand where things come from and why it's natural to take these things. Yeah. So, anyways, I take the octagon, and it's supposed to be the Minkowski sum of how many hypersimplices of type B2? Two. Okay, interesting. And what are these hypersimplices? I should take these fundamental weights, and I should permute them. So the fundamental weights lie. This is omega 1. This is omega 2, right? So if I reflect omega 1 across all of these lines, what do I get? Say it again. Square. Okay. And I get a square for omega 1 plus a smaller square for omega 2. Right, sorry, these should be omega 2, omega 1, 2. And you can check that octagon is indeed the Minkowski sum of these two squares. So yeah, that's out of time. So that's, and you can actually, yeah, let me say one last thing is that the type A3 permutohedron is, or maybe, yeah, for each of these larger root systems, you actually get each giant permutohedron as a sum of some nice hypersimplices. Anyway, it works in all dimensions, and it's beautiful. So I'm going to see you all on Monday. Everybody have a nice weekend. See you soon.